Hello and a very warm welcome to this talk on ARM's SeeWare machine learning and computer vision solution and how we've deployed it to address COVID-19 security issues at the landing in Media City, UK, Salford. My name, as John said, is David McCaffrey. That's my headshot in the bottom right of the slide, and I'm sure I'm visible to you in one of the windows in Zoom. I've got my video on. I'm the product manager for computer vision and machine learning at the world-leading UK chip design company ARM, so that explains the pun in the title of the talk. To start with, I'd like to draw your attention to the green bounding boxes around the standing figures around the table in the opening slide graphic. Without the aid of the boxes, your eyes and brain are capable, through tens of millions of millennia of genetic evolution followed by a year or two of childhood learning, of identifying that the arrangement of coloured pixels within those boxes represents upright human figures viewed from top down. You've never seen those people before, and you don't even have a very good viewpoint of them, but you still know that there are 5 people in that image. So this talk will focus on computer models, so-called deep neural network models, which can be trained to do the same thing, recognize and locate objects that they've never seen before in the context of an image that they've never seen before. And the bounding box is one form of output from such a model, telling a human user what class of thing the model has identified, where that thing's located in the video or still camera image. And you'll see bounding boxes reappearing in many places in the rest of this talk. These deep neural network vision models and the machine learning technology in which they're based, they're at the forefront of the latest phase of the IT technological revolution. That revolution has so far seen computer vision models deployed at scale in the centre of the internet by the social media giants to detect things, mostly cats, in image and video data uploaded by us to their cloud servers. At the ARM Insight Group, we're at the next stage in this revolution, taking these models and building the Internet of Things, the IoT platforms, to deploy them securely in machine learning applications running at the edge of the internet on smart compute devices in ways which respect privacy and personal data. The vast majority of the video data which is currently collected by camera-enabled devices goes unanalyzed due to the lack of bandwidth to send it to be processed at the centre of the internet. So by moving the ML processing to the edge of the internet, that unstructured vision data can be accessed, transformed into structured, low-density inference data, and then sent from edge to cloud to analytics applications where it can inform and optimize real-time action. In this talk, I'll explain how we've deployed ML computer vision at the edge to help the managers of the landing in Salford Media City to monitor their building occupancy levels in real time and put in place alerts and analytics to support COVID security. So who is ARM? For those who don't know, haven't seen us recently in the news, we were founded in Cambridge in 1990 as a spin-out from Acorn Computers with a focus on designing chips with low power consumption requirements. This focus came into its own with the advent of the smartphone, where maximising compute for the lowest possible battery consumption is the name of the game. Our licensed chip designs are now in almost every smartphone on the planet, expanded into a range of other devices as the engineering imperative to extract more compute for less power proceeds remorselessly. As of February this year, 160 billion ARM designed chips have been shipped in total. And during this 60-minute presentation, another 3 million devices will be shipped with ARM design chips on board. And who is the ARM Insight Group? Well, we're a 30-strong group within ARM's Tech Hub in Manchester. Our office is in Portland Square. We're focused on machine learning, ML, computer vision technology, and in particular in building the engineering platform to train, deploy, and manage ML vision applications running at the edge of the internet. So why the edge? I already mentioned this in the introduction, but because that's the only place where the huge volumes of dense video stream data generated by the growing wave of video-enabled IoT devices can be processed. The Internet of Things is connecting video-enabled devices to the internet at an exponential rate. These projections in the slide are from before COVID, and who knows what they are now after the onset of COVID and the acceleration of the digital transformation. But prior to COVID, the projection for the number of devices containing an ARM chip, most of which are, or many of which are video enabled, was estimated to reach 1 trillion devices in 15 years from now. Only 10% of the video data generated by today's connected devices is currently analysed. So the untapped opportunity for extracting inferences about what's happening in the world using data from video-enabled edge devices is huge. And the ML to computations to extract that can only be performed at the edge. The internet will never have the bandwidth to transport that quantity of raw video data to the centre. The other piece of the jigsaw that comes together at the moment is the GPU, graphics processing unit, accelerated smart devices, edge devices in which to perform this machine learning computation. These devices are now available and the deployment is growing. So the ARM Insight Group is focused on building the engineering platform in which to do that edge-based ML computer vision. And what is that platform? We call it SeeWare, so sorry for another wordplay. And we have various vertical applications built on top of this platform which are delivering ML vision solutions into retail, healthcare, smart cities, and in the specific area of traffic management. And then the subject of today's talk, smart buildings. So we'll come on later to what we mean by computer vision for smart buildings, but some basics to start with for those of you that are not technical experts in neural networks and machine learning. So what is a machine learning computer vision model? I'll make three broad points in this slide. First, neural networks, or more correctly, artificial neural networks, have been around for a while, as shown in the left-hand column. Now, true neural networks, which are, animal brains, the brains of you and me and other animals, these have been around for a very long time. But the artificial kind have been around since the 40s, when they were first proposed as a mathematical model of learning processes by neuroscientists and psychologists. Deep neural networks, which means multi-layered versions of such networks, they've been around since the 60s, when the advent of powerful mainframe computers first made practical the implementation of the algorithms that are required to train these networks. The objective of training such a network is to encode it with what's called generalizable knowledge. In other words, to avoid overfitting on the training data, allow it to operate on unseen data so that it's capable of generating the expected set of responses from a set of inputs which it hasn't seen before, but which are similar in some sense, some statistical sense, to inputs which it's seen in the training set. So going back to my example from the introduction, if we have a model which has been trained to detect humans by being shown a limited set of images of some specific humans, like the ones which were on the introductory slide, then a well-trained neural network model should have been trained on images of a limited set of humans. A well-trained neural network model should be able to identify other humans from images which it has never seen before, by recognizing genetic learned features of what a human looks like, whatever that means. A trained network is thus able to make inferences from data that it's not previously been presented with. The development of neural networks, which is the vision thread of neural network developments, is set out in this timeline. The development stalled a number of times, and the promises of the technology have failed to materialize a number of times in the past. But these blockages have disappeared in the last 10 years with the advent of increasing amounts of cheap computing power. In particular, they realized that GPUs, graphics cards, the kind of things that power gaming platforms, that they could be used to perform the massive parallel computations that are required to train and perform inference on neural network models. The other blocker which disappeared in the last 10 years was the access to the required volumes of data to train these networks. The required volumes became available to researchers working at the big social media and IT companies in the form of the vast amounts of annotated image, video and text data which you and I have uploaded. You can see Google and Microsoft mentioned on the list on the left-hand side as pioneers of recent deep neural network development in fields of vision and speech recognition. And lastly, those same companies and their academic collaborators have developed efficient open source AI programming frameworks like TensorFlow from Google, which have massively reduced the engineering time and effort required to program and train these models. So the result is a set of powerful open source computer vision models which are now capable of performing real-world vision tasks in real time. The second point on this slide is what does a machine learning computer vision model actually do? Well, after being trained, it does at least two things as shown in the middle column. So it does basic image detection and classification, which means if we present a neural network with a set of pixels which represent a digital image containing only one object, such as the dog shown here, and we ask it to classify what those pixels represent, then it should come up with a list of things of what it thinks is in the image, with probabilistic assessments against the probability of the image being each of those things. And the classification which is selected is the one with the highest probability. The training process adapts the parameter weights in the layers of the network so that the network learns to map the raw pixels to abstract representations of the visual features of the image. So it maps the pixels into the arrangements of edges and corners and connected regions of colour, light and shade, etc. that appear in the image. And then it learns to classify that feature map in terms of whether it represents a dog or a cat or a bike or one of the other objects it's been trained to recognise. And in the bottom of the middle column, more sophisticated models are able to detect multiple objects in an image and identify the regions where those objects are within the image. So when presented with an image with multiple objects, it's able to put bounding boxes around regions of the image which contain an object that it recognises. This is where the bounding boxes come in. The last point, as indicated in the third column, is what data is required to train these models. Well, the models in current usage are generally trained on very large open source sets of image data, mostly collected and made available, as mentioned above, from social media sources. One such example is the COCO image set, which is an open source data set consisting of over 200,000 labelled images containing 1.5 million objects belonging to 80 object classes, things like people, table, chairs, dogs, cats, etc. And 91 stuff categories like water, grass, sand, so on. So the key point is that these models have been trained to recognise people in their generic form. They're not doing any form of facial recognition or identification of individual people. The technology can be taken and developed into specific forms of facial or biometric recognition, but not by ARM. Our implementation of this technology is based on designing in the privacy and security of personal data from the start. And I'll come back to that point later. So how does it work in action? Well, here's a demo video, and you're about to see the bounding boxes again. So if I let this video run for a few seconds and then pause it and talk about what's in it. So what we have here is an office scene. It's been shot with actors. It's on a video loop that loops every minute or so, and the stream is being fed to a machine learning detection model, which is running on a virtual graphics card enabled gateway. So a virtual machine in the cloud with a graphics card in it. That model is detecting people and also chairs and tables in the video stream in real time. So as the video is playing, it's detecting people and other objects in the video. The detected people are identified with bounding boxes, the light blue ones that you can see. The dark blue ones are chairs. The label on the box shows the class of detection. The label shows the percentage confidence of the detection. So the model gets less confident if the image is partially occluded or badly lit. And like the man in the top, actually he's quite, the man in the top right, he's partially occluded by the light shade, although the confidence is still quite high. It gets more confident if the image is clear and unoccluded. The lady in the top left, she's not being detected at the moment because her hair colour and the white shirt that she's wearing blends in with the background. From time to time she is detected when she moves her arms out from her side. The model becomes more confident that's a person when she moves to the left so that she's in front of the dark background of the filing cabinet. Again, it becomes more confident and it detects her. But there's a confidence threshold set to some level, and below that confidence level we don't display the model is actually still detecting her, but it's a confidence level of I think below 40%, so it's not displaying the detection. The images don't leave the gateway. In normal operating mode, only the metadata from the models are leaving the gateway. So that's the bounding boxes and the classes of detection. Now, if I pause the video again. So what we're now seeing, so we switched from the raw video overlaid with the bounding boxes. As I said, the inference output in the form that a person or a chair or something was detected in a given pixel region of the image, that's sent up to the cloud layer. And what you see in the left is the aggregation of that data in the cloud layer into a database and displayed in a dashboard. So the top chart here is showing the total occupancy for the office space being surveyed by the camera, which is around about 6 people. It varies between 5 and 7, depending on who's moving in and out of the image. And it drops to 0 every time the loop of video restarts every minute or so. So it's displaying the total occupancy for the office space, and it's displaying the history on a time series chart. On the right, what you see is our mobile application. Now this is used in configuration mode to allow limited access to the video stream overlaid with the detection boxes. It allows us to define what are called detection zones. These apply a semantic context to the image and allows the computer a richer set of occupancy analytics based on the meaning associated with a person being in one or other part of the image. So here what we see in with the pixel mask in blue is that we've defined that area of the blue masked area of the image as representing the upper left office. So any person detections which occur in that zone of the image are tagged when they arrive in the cloud with the location of upper left office, and then those detections can be summed. Start the video again, you'll see it. Those detections can be summed to give the specific occupancy in that area of the video, and you just see that there's page down to it that's gone past it now to the upper left office. It's now highlighting the red area corresponding to the upper right office, and you see the time series for the upper right office, and bottom mid right office and corridor. Now, if I pause the video again, what's going to happen next is that the person doing the demo has deleted the mask which was corresponding to the upper right office, and they're going to recreate it. So this is reconfiguring the cloud analytics layer dynamically without changing the underlying configuration of the camera or the machine learning model. So the pixel mask has been deleted, and then what's going to happen next is that the user of the mobile app is going to rubber band to define the whole of the field of view as a mask, which is now relabeled as the upper left office. And now what happens is the detections anywhere in the field of view are tagged as upper left office, and you see in the time series chart that the occupancy has jumped from somewhere between 0 and 1 up to between 6 and 7. So it's now tagging all of the occupants in the field of view as if they were in the top left office, and now the user's gone back and they've deleted that again and they've gone back to the original configuration. And when they create that mask, you'll see in real time that the occupancy count drops back down again. And it's back to detecting the lady in white intermittently. We'll go over and there you go. It's got the first count again of one person in the upper left office. So that's one example of creating analytics in the cloud layer on top of the detailed detections coming from the occupancy model. So to recap, what's the network architecture which achieves that the detections and inferences shown in the video? So at the bottom level, we've got cameras, IP cameras, which are feeding into smart gateways. These are compute devices, GPU acceleration, which are running the ML models, which are analyzing the video stream to detect and localize people and other objects within the video stream. The inference data as to what's in, what objects are in the video image and where they're located in the image in pixel terms, that's fed up to as raw detection metadata to the cloud layer, where it's then enhanced with, for instance, tagging with location, other forms of enhancement, like computing dwell times to measure how long a person stayed in a given zone or things like that. It's enhanced and aggregated into analytic applications and served out in the top layer to in dashboards, in mobile alerts, and to third-party systems for analytics. And we do this in a way which builds security and privacy into the design in two key respects. First, as shown in the diagram here, mentioned a number of times already, no video or image data leaves the edge device. So the video data flows from the camera to the gateway, but the gateway is in the same physical location as the camera. The video data doesn't travel beyond that. The ML model, which processes the video stream, runs on that gateway and at the edge of the internet. Only encrypted inference metadata like numbers and classes of detected objects in each frame leave the gateway and are sent up to the cloud. And secondly, we approach both video data and the inference metadata generated from it as being intrinsically personal. And we approach the design of our applications to be compatible with GDPR obligations. Particularly, we help users of our computer vision technology through the implementation approach and through the completion of the DPIA to use video data generated by their cameras located in their premises, to use such data in ways which are covered by legitimate interest and which properly respect the personal nature of the data. And to repeat, there's no facial recognition of any form or any other type of biometric identification being performed by ARM's ML vision models. No vision data or direct identifiers are recorded or stored anywhere in the system. So how do we bring this technology together into a specific solution for smart buildings? Well, the core offer is targeted at deploying this technology to deliver benefits to facilities and office management users using either existing IP cameras, so-called brownfield, or new camera installations, greenfield. The economic business case is driven by using ML vision to firstly increase office efficiency in terms of more efficient use of the space and reduction of carbon footprint. And secondly, better real-time control of the building. So even prior to COVID, many office buildings were only partially occupied in practice. Despite every desk space being filled by a named occupant, many desks sit vacant for large proportions of the week due to people needing to work out of the office for various reasons. By being able to gather accurate data on how many people use which bits of the building, when they use them, then the allocation of space and the delivery of heating, lighting, fresh air, etc., to different parts of the building can all be optimized. And by monitoring the usage of the space in real time, occupants can be notified as to where there are bottlenecks in the lift system or the corridors, when the canteens are free, where they can find vacant hot desks and so on, thus improving the real time control of the building for the benefit of its users. In one application which we implemented pre-COVID for an operator of a flexible working hot desking space in Dublin, we installed this technology of cameras and ML models to detect which hot desks were occupied, which unoccupied, and this delivered real-time information to the users of the space as to where to find a free desk. It also generated valuable analytical data for the operator of the space to optimize the desk layout to maximize the achieved occupancy. People like a certain distance between themselves and their neighbours when they're sitting at desks or whatever, and they won't sit in a space between two occupied desks if the desks are packed too tightly and that space is too narrow. So whilst in theory a certain layout might achieve an occupancy of 8, in practice they might only achieve 5 due to customers being unwilling to fill the gaps in a tight layout. The operators were able to experiment with different layouts and find the one which generated the highest achieved occupancy using the occupancy history data generated by the camera ML system. Now there are of course other sensors, some cheaper, such as PIRs, pressure pads, etc., for determining whether a given desk is occupied or vacant. But one of the advantages of a camera-based system is that it allows the desk layout to be rearranged and still monitor for occupancy without needing to reconfigure or reposition the physical sensor hardware or retune the detection models. All that's required is to soft redefine the detection zones in the cloud layer, as I demoed earlier in the video. The detection zones which represent the different desk areas in the field of view. If you move the desk, you just redefine the pixel masks which represent the new positions of the desks. So what was the specific smart building solution for the landing? Media City UK in Salford. Well, the landing, as you may know, is an office building in Media City UK. It gives tech and digital startups and SMEs a place to work alongside the large media and tech organisations that are based there, allowing them to benefit from the network effects of that digital hub. There's around 120 businesses occupying the building, a mix of tenanted and flexible working spaces. And our technology was installed on the 7th floor, which is shown here in the floor plan. The 7th floor is a communal meeting room and socialisation space for tenants in the building and for outside users. There's a variety of bookable meeting rooms in terms of style, capacity, configuration, and a bar lounge area for informal socialising. We fitted the 7th floor space out with 12 axis 3058 dome cameras in the locations indicated by the black circles on the floor plan. These are 12 megapixel fisheye 360-degree IP cameras. They can deliver up to 30 frames per second. They have de-warping software which takes the fisheye view and splits up into 4 separate configurable pan-tilt zoom streams per camera. Each of those streams with 5 megapixel resolution and a wide dynamic range. The cameras were all wall mounted towards the tops of walls to give complete coverage of the meeting room, and multiple streams were set up in the cameras to cover the space. We've changed the configuration a number of times, but somewhere between 14 and 18 streams were created out of the 12 cameras. We also installed 3 Jetson AGX Smart Edge devices. These are edge compute devices which run the ML models. They're equipped with 8-core ARM V8 64-bit CPUs with 512-core Volta NVIDIA GPUs, graphics cards. They've got 32 gigs of RAM on them, Linux operating system, and they support the runtime libraries which are required to execute machine learning models in inference mode and allow them to leverage the GPU compute resources of the box. So in particular, they support the NVIDIA Jetpack SDK and the TensorRT runtime software library. The inference data generated by the ML models running in these gateways is fed up in real time to the landing's tenant account and database running in the SeeWare cloud application, which is hosted as a SaaS on MS Azure. Now, the installation went in just before the outbreak of COVID, as John mentioned in the introduction. And initially it targeted requirements addressing questions around how the meeting rooms were used. So specifically, we were looking at questions around what's the average occupancy of each meeting room, and how did that compare to the capacity of the room in the booking system. And critically for the landing, because they wanted to understand this particular aspect of usage, what distribution of distinct people and dwell time gives rise to a given average occupancy. So as shown in the slide, the same average occupancy for a room over a period of time can mask radically different underlying distributions of usage patterns. And that gives key information on which to plan ancillary services like catering, consumables, toilet facilities, cleaning, access facilities, and so on. Other questions were how long were the rooms used for, how did that compare to the booked reservation time, and as a consequence, what's the scope for maybe overbooking the start-end period of meetings in the same room. Meetings tend to finish early, maybe you can overbook the start of the next meeting room if you're looking to maximise utilisation of your meeting room space. How often do non-booked meetings occur? How often do people squat in rooms which they haven't booked? What's the rate of no-shows in meeting room bookings? So those were the types of questions which were envisaged when the system was first installed and configured. Then COVID came along and that changed the focus to giving users of the space confidence. After lockdown finished in June or whenever the planning started on the reopening process, the focus changed to giving users of the space confidence that the space is safe to use. So that confidence falls under different headings. Safe occupancy level monitoring, that's about monitoring each of the individual rooms and alerting that when it approaches or reaches the maximum limit consistent with social distancing. So that's not the original published meeting room capacities. That's new capacities which are consistent with the people in the room maintaining appropriate social distance. Publication of safety status to potential users. Well, that's about displaying the current occupancy levels on dashboards, on websites where potential users on other floors of the building can see that the space is safe, safe occupancy levels, and that it's an appropriate time for them to come and use the facilities. Alerting when safe levels are close to being compromised. That's about generating real-time alerts via mobile apps or other means to the management of the landing so that they can take action when capacities in the rooms are getting close to unsafe levels. Face mask compliance is about monitoring compliance of face masks and prompting users to comply in areas of the space where face mask usage is required. And social distance compliance is about monitoring individual social distancing behaviours so as to generate analytics on where congestion points occur and how to remediate them. So what do users of the system actually see? Well, as mentioned earlier, they don't see the raw video, nor do they see the bounding box detections overlaid in the video. The bounding box detections can be accessed in the mobile app, as I showed you in the video, during configuration mode, but in production mode, only the detection metadata is sent up in real time to the cloud, like the fact that detections of class equals person have occurred at such and such pixel locations in frame X from camera Y. That's the information that goes up to the cloud. These detections are tagged with locations corresponding to the rooms based on the stream ID in the detection zone in which the detection was recorded. And then detections with the same location tag and timestamp are summed up to give the occupancy count for each location. So this is what you see in the dashboard with counts overlaid on the plan. So I took this screenshot from earlier today. There's some filming going on in the screening room. So there's 2 people in the screening room, 1 in the bar. You see that overlaid in the floor plan, the utilization is at 3% as a percentage of the total safe capacity of the floor. And you can see the time series chart on the bottom showing the history of total occupancy for the whole space. I had hoped at this point to give you a live demo of the, if I just switch over to this web page, this is the feed coming live from the landing. 2 minutes ago there was, or maybe 5 minutes ago there were people there, but at the moment there's no one. You can see there was someone there, 1:34. This data is updating every 15 seconds, I think. Now from there we can drill down and look at, we can click into a specific room and see what's the occupancy in that particular room. Again, we see the history there, there's no one there at the moment. We can drill down into the bar area. There's not been anyone there. So I'll go back to my screenshots that I captured earlier when there were some people around. The dashboard is available to managers of landing in the first instance, so they can see what the occupancy is for each room and what the history is. And the floor plan widget is also, not the time series, just the floor plan widget in the center, is planned to be displayed on the landing's external website, so that users on other floors of the building can see when the 7th floor is at safe occupancy levels and can decide to go there for a coffee or an informal meeting or to use the workspace or whatever. The safe capacity level for each room is stored as config in the cloud database. So the occupancy counters are color coded to turn amber and red when the occupancy level gets close to or exceeds the safe limit. Again, there's limited usage of the 7th floor at the moment, so I can't show you the color coding working. And as I just showed you in the live demo, you can click into the individual rooms and see the history for, this one's a screening room. This is the multi-stream display. So for the bar area, there's 4 streams covering that area. So we see the total at the top. There's been 1 person in and out of the bar area, and they've been in the area covered by camera 9, stream 1. if the admin user was to configure additional detection zones in a given location, then the time series and speedos for those locations would automatically appear on the dashboard for that location. The landing management can also receive alerts for near capacity and over capacity for each location via the mobile app. The next steps after this are to look at, if you just play this video, the next steps are to look at face mask compliance in the locations where that be required, such as the lift, lobby, entrance corridor and so on, and in social distancing compliance. So the face mask compliance model combines 4 detections. There's a person detection. You can see here that our head of, if I just pause it at this point, you can see our head of AI technology. It's detected the person with a confidence of 99%. You can see there's also a green outline around his body. That's another form of model output, which is called a semantic mask. It's highlighting the pixel area which corresponds to the outline of the detected object. The inferences are generated if a person is detected but a mask is not detected, then the inference is that they're not wearing a mask. And then there's a mouth and nose detection. You'll see this coming next. If a mask is detected but the model is also able to detect the mouth or the nose, then the inference is that they're not wearing it properly. Okay. And then the inferences from the face mask model are fed to a local display to give immediate green smiley face or red warning to nudge people to comply. Analytics on percentage compliance are also generated. And then the social distancing application, this detects people in an image and measures the distance between them and alerts if that distance is less than some configurable social distancing threshold. So this works by projective transformation. The midpoint of the bottom of the bounding box of each detected person represents their feet. We know the coordinates of the feet in the plane of the camera field of vision, field of view. We can do a projective geometry transformation to determine the corresponding coordinates of the feet on the plane corresponding to the ground in the real world, and then we can measure the distance from that person's feet on the ground plane to other people's feet on the ground plane. So what you see here is the detections go red when or a pair of detections will go red when they come within less than the social distancing radius of one another. And on the right, you see the top-down view, again with red links between detections which are within less than the social distancing radius of one another. So the aim here is not to prompt some manager to go and break up groups of people. For one thing, it's not really possible from video data alone to determine if a group of non-distance people are a family or a bubble. Rather, the aim is to gather analytics on where in the geometry of some area of people flow do the pinch points and cluster points occur, where people find it difficult to maintain social distance, in order to help with the design of the physical layout of these flow routes. So by analysing the analytics from this stream, for instance, it could be determined that the positioning of the seats in the pavement and the phone boxes are causing constriction points where people clump together. So to summarise, SeeWare is supporting safe post-COVID opening at the 7th floor of the landing with edge-based machine learning computer vision. The images are processed by machine learning models running in smart gateways, which are physically located in the landing's premises next to the cameras. No image data leaves their premises. That makes it safe by design. We've been through an extensive GDPR, DPIA process with them, so they're clear as to the uses to which they're putting the data, and it's properly covered by legitimate purpose. The landing are only consuming low bandwidth to send the inference metadata from these models up to their cloud database account, where it's then processed into analytics to support real-time action to maintain safe occupancy levels for the space as a whole and targeted to individual locations within the space and individual rooms. And it works with standard IP cameras, which once installed will continue to support changes in the targeted use cases, such as the switch from pre to post-COVID requirements of switching from measuring how the meeting rooms are used to measuring safe occupancy levels. That switch was done without reconfiguring the physical cameras or the underlying machine learning detection models. And that camera infrastructure will continue to support advances in the detection capabilities of the models which are processing those camera streams as we go forward. We're able to deploy new models to those gateways as the models are developed and enhanced. And the models themselves are configurable and extensible to cover new use cases such as the last couple that I outlined of face mask compliance, social distance compliance. And they've been fine-tuned to solve the real-world problems of detecting people and monitoring occupancy levels at the landing. So with that, I would thank you for your attention and for listening to me, and we'll open up at this point to any questions.